Welcome back to ECE 220. Group A, your labs begin for lab number 2 today, and they continue through Friday depending on your section. Group B, your report is due tomorrow for lab number 1, and your pre-lab for lab number 2 is due on Saturday. We're in op amps, and don't forget, if you're interested in advanced standing, yeah, you're wondering what's under the goals, but if you're interested in advanced standing, please take care of that this month. You have until the 25th of October. What I want to do today is continue examining different circuits that are possible by using op amps. Now we have a different way of creating more interesting circuits than just with resistors. We'll start with an exercise, and we're trying to find V8. So I guess I was needing some inspiration. So I needed a V8. I don't know, maybe that's too long ago, but did you ever see the commercial, oh, I could have had a V8? So we're going to try to find V8 this morning. We will summarize where we finished last time with the inverting summing amplifier. Then we will try to get to a few more circuits, one being the non-inverting amplifier circuit, and a special case of that is a buffer circuit, or it may be referred to, depending on the literature you're looking at, as a voltage follower circuit. Then we will look at putting these two pieces together, essentially, the inverting and the non-inverting. So now we'll apply voltages to both of those through resistors interconnected in certain ways to come up with a difference amplifier. That's where we're headed. To begin, let's have you find V8. V8 is now, where did that come from? It's associated with the 8K ohm resistor in this circuit. That's voltage across that 8K ohm, referenced positive to negative, left to right. So I want you now, based on what we've discussed so far relative to op amps, I want you to find V sub 8. And I will give you, let's say, a couple of minutes, maybe 3, to find V sub 8. I was expecting to see a lot of refreshing faces after finding V8. Are there some wrinkles on this relative to what we've done up to this point? Is there anything a little different than what we've talked about in this circuit? What was your very first step in the analysis for this problem? What was the first thing that you tried to find before you even found V8, or in the process? What was your first step? What's the first thing that we want to look at or determine before we go too far into our analysis approach? Do you remember the flame that we were trying to stick our hand near? And if we get too close, what do? We retract. We have some negative feedback. Is there feedback, and is it negative? Are we connecting the output pin to the inverting pin of this op amp? And if so, then we can start making some assumptions for the analysis that we will then perform. In this case, there is. And what did you do with the, and I might just refer to that as NFB. That'll make our text messages a little shorter when we communicate. You might want PFB in your communications. What's PFB? What's the opposite of negative? Positive. You probably want your messages to be positive. Positive feedback is probably what you want, but in this case, we want negative feedback, NFB, and what did you do with that 5K ohm resistor connected to the non-inverting terminal? What did you do with that? Was that something new? Have we dealt with that? Boy, you guys didn't have your V8. Should be all energized. What's the current going into the non-inverting input pin? What's this current? Zero. Because there's infinite impedance in the ideal case. We have I sub p is equal to 0. What's that mean about the voltage dropped across that 5K ohm resistor? There is no voltage drop. There's no current. So now what can we conclude about V sub p? Hopefully you can say that's 0. That's our common node value. And with negative feedback, now we have V sub p equaling to V sub n. And now we know that V sub n is equal to V sub p, and it's 0. We wanted V sub 8, which is a little different than finding V naught, but V sub p, I knew that was going to happen. And V sub n is there. A lot of times they want you to do the analysis on the circuit. That's sort of what I'm doing now. I'm kind of doing my thinking on the circuit itself. If we now look at this a little bit more carefully before we go too much further, do you see if I actually performed a KVL from here up through there and down through there and then back, I would have a connection or a relationship between V sub 8, V sub n, and V sub 0. And I know V sub n is 0. Doing the KVL, I have minus Vn plus V8 plus V sub 0, and then I'm back where I started. So in this case, KVL allows me to say that minus Vn plus V8 plus V sub 0 is equal to 0, or I've concluded that is 0. Now I know that V8 is in fact minus V0. And this circuit was actually a inverting amplifier. The gain was 4. We input 1, so we should be getting a minus 4 out at V0. Now we know what V8 is. It's the negative of that. So tonight you need to verify that V8 is now minus a minus 4 or 4 volts. Gives you something to do. And that V0 being at minus 4 is within the power supply rails. We didn't saturate. We will see V0 of minus 4 volts and V8 then, which is the voltage dropped from left to right across that feedback resistor, is in fact 4 volts. What about this circuit? This is where we left off last time. Now what we're doing is we're expanding upon what we are injecting signal-wise into the inverting pin of our op-amp. And we now have 3 different voltages identified. We could have 4, we could have 8. We could sum up a lot of different voltages at the output. We would need to worry about whether we are saturating or not with that sum, but we now can interconnect many different voltage sources into this inverting op-amp configuration. What do we have here? What's the output equation? Do you remember? Or could you derive it quickly? What's the first step you want to make? Step 1. What question do you need to answer? Is there negative feedback? Is there? Yes. We have a connection between the output pin and the inverting pin through R sub F. We do have negative feedback. Now that we have negative feedback, we'll just make the assumption that V sub P is equal to V sub N. And that now allows us to write KCL at V sub N. So now we're going to assume that, and V sub P is actually equal to 0. It's connected to our common node. And performing KCL here, at V sub n with V sub n equal to 0 gives us our output equation. Now we have 0 minus V sub a over R sub a plus 0 minus V sub b over R sub b plus 0 minus V sub c over R sub c plus 0 minus V sub 0 over R sub f equals 0. And aren't you glad I just put 3 voltage sources? But do you see you could have 10 of those? You could have 4. You could have 2. But that's the KCL equation. If we now multiply all the terms by R sub f and put the V naught to one side or the opposite side, we end up with V naught is now equal to, and I'm going to factor out the negative sign, R sub f over R sub a, V sub a, plus R sub f over R sub b, V sub b, plus R sub f over R sub c, V sub c. And that's now the output equation for this inverting summing amplifier. And you can now weight those voltages, A, B, and C, with different amounts depending on how you select your resistors, RA, RB, RC, and R sub F. If we go ahead and pick all of those resistors to be the same value, if R sub F is equal to R sub A, R sub B, and R sub C, all of those ratios become 1. Or now we simply are negating the sum of voltages A through C. And that's now the special case. We have the output voltage being minus V sub A plus V sub B plus V sub C. And I wanted to make sure that you heard that. I mentioned that as you were packing up and leaving at the end of last period, and you maybe didn't hear that. But now we have a way of combining voltages, either weighted sums or even without weighting. But what could happen in this scenario in practice? What are we banking on in this special case? That our resistor values are equal. And we know from the lab that that's not necessarily the case. But you could get finer tolerance resistors to help minimize that difference, but you still might have some slight ratios there that are different from 1. But in general, if it's close, this is what we have. Let's now look at a different circuit. Let's look at a non-inverting amplifier circuit. And this is what the name implies. We're hoping that the output now is not an inverted version, an inverted scaled version of our input. We want it to be non-inverted. And now we have our input voltage being injected into or applied through the non-inverting pin of our op-amp. The input now is V sub G, and that's going into the non-inverting pin. We want to now derive this formula or the expression for the non-inverting amplifier circuit. But the process, the steps, are very similar. What do we want to first establish? Step 1, negative feedback. So now we have, in our analysis, we say, okay, we have negative feedback. That now allows, because we're assuming we're living with an ideal op-amp, now that gain A is infinite, and that's now with negative feedback, it's trying to drive the voltage difference between the non-inverting pin and the inverting pin to 0. Or we're trying to force V sub P equal to V sub N. The negative feedback then allows us to assume V sub P minus V sub N is equal to 0, or V sub P is equal to V sub N. What is V sub P? That's now this voltage. So we take our voltmeter and we apply the positive lead to the non-inverting pin, and we connect the negative lead to the common node in this circuit and measure V sub P. What are we going to see at V sub P? Is it related to anything in this circuit? And what's maybe the next thought that enters your process of analysis? How do you find V sub P? You could do a KVL because you have V sub G and you have R sub G. You could do a KVL in that little loop there, and you would now need V sub P could differ from V sub G based on the voltage dropped across R sub G. Do you know what the voltage dropped across R sub G is? Well, I need the current. What's the current through R sub G? Even though I have a source there, there's no current going into that op-amp because it has such a high impedance or resistance. This I sub P is 0. What's that force V sub P to equal? V sub G. So in the second step of this analysis, we can say that V sub P is equal to V sub G, and we just found from the negative feedback assumption that that's also V sub N. And now we can use that equality between V sub P, V sub G, and V sub N. They're the same. Let's just call V sub N V sub G when we're using that in what? Step 2, which is the KCL at that inverting pin of our op-amp. Let's now write KCL at that node. And let's sum all the currents out of that node, so that this particular node has a voltage of V sub G. The current going left through R sub S, V sub G, the voltage where we're at, we go to the other side of that resistor, the voltage is 0, so we have V sub G minus 0 divided by R sub S. The current leaving that node through R sub F, V sub G minus V sub 0 over R sub F. And what's the current going into the inverting pin of the op-amp? It's 0, isn't it? We now have our relationship from KCL. we said we had V sub g minus 0 over R sub s plus V sub g minus V sub 0 over R sub f plus 0. This was the I sub n equaling 0. Little algebra gives us that. We can clean that up even more by multiplying both sides through by R sub f, and that will isolate the output voltage that we want. We want to know, how does the output voltage relate to the input voltage that was applied, and that was V sub g. And we have it if we simply multiply everything by R sub f. Now V sub 0, and I'm going to now just interchange the order of that sum. Now I have R sub f over R sub f as one of the terms. I'm going to call that 1. And that's then added to R sub f over R sub f. R sub s. Wow, I really have to enunciate. So this is 1 plus R sub f over R sub s V sub g. And that gives us then the formula or the expression that we need for this interconnected op-amp. And this is a non-inverting amplifier. If we look at that formula, what can we extract from that relative to some useful information? What are some observations? I hope you see that our resistors are both positive. We're adding a ratio of positive numbers to 1, and we're using that to scale V sub g. Question? What? So now the comment, I don't think it was really a question, it was an observation that if you make R sub f equal to 0, what does that mean? If R sub f is 0 in our circuit. In the formula, what does it say? That just says that the output is equal to the input. If R sub f is 0. Is that possible? Can we make R sub f equal to 0? What does that do in this circuit? R sub f has 0 resistance. That's now a pure wire, isn't it? And that's our next circuit that we're going to build. It's going to be a buffer circuit. So before we get there, that wasn't set up, really. That wasn't a plant. That question or comment was not a plant. But now we can modify this so that if we wanted the input and the output to be equal, we could do it by forcing or just placing a pure wire between the output and the inverting pin. And now you might say, why do we want to do that? We already got the input. Why do we want the input again? The input voltage. We'll get there. Just before we get there, let's make some observations with R sub f not equal to 0. With R sub f not equal to 0, do you see that this formula, this gain, which is 1 plus R sub f over R sub g, doesn't involve the gain of the op-amp. Doesn't involve capital A, which is huge, but that's good because your A might be different from my A, although I'm sure they're both block A's. Go Wildcats. Anyway, where were we? Trying to make some observations. Is the load resistance involved here? We didn't even have a load resistor here, but we could put that, attach that. Did that have any bearing on the formula? No, but what do we need to be cautious of? with respect to R sub L. Can we just make that a wire? You can't see my facial expressions on the video. Probably a good thing. But R sub L has a limit, doesn't it? Because this poor op-amp can't give us an unlimited amount of current. So we can't just go really low with R sub L. So there is a lower limit. But the gain formula did not depend on R sub L, the load, to a point. There's a lower limit. And that's due to the if you look at the data sheet, you're going to find that all op-amps have a particular limit to their output current that they can supply or that they can deliver. The 741 is maxed at about 40 milliamps. So you can't just connect any load to a circuit, but that's some observations. When can we expect linear operation? When do we not have, or what's the condition that we're in when we are not in the linear operating region? What do we call that? If we're not operating in the linear operating region, what are we operating in? Saturation, either on the positive side or the negative side. And how do we avoid saturation? So saturation is, how do I want to say this? If our system tries to go beyond the supply rails, so our gain might try to push us. Let's say our gain was 4. Well, it doesn't really matter. Suppose the gain was something, and we calculated from that gain that our output should be 25. And in fact, the supply rail voltages were 10. We know we're in saturation. So it's a combination of the supply voltages at the rails and the resistor values that we're hanging on to that. That's what influences saturation. In this case, what's the highest that V sub 0 could become? Let's say that our supply rails are equal. They're plus and minus V sub CC. How big can V sub 0 get? It could only go as high as one of those VCCs, either positive or negative. That's where it lives. It's bounded by VCC on the top and minus VCC on the bottom. If that's the case, then we know that all of this linear operation depends on 1 plus R sub F over R sub S V sub G, that magnitude being less than VCC. But that we can divide out the input voltage and say that, 1 plus R sub F over R sub S, which we know is positive, is less than VCC over V sub G's magnitude. When you're picking R sub S and R sub F, and if you know V sub G and you know V sub CC, you need to observe this relationship to avoid saturation. You need 1 plus R sub F over R sub S to be less than VCC over V sub G. Suppose VCC was 20, and you want V sub G to max out at 5. What's the constraint on 1 plus R sub F over R sub S? VCC is 20. Little v sub G, you're saying its max is going to be 5. Now you know that that 1 plus R sub F over R sub S can't be bigger than 4. So you need to pick those resistors such that R sub F over R sub S is less than 3. Is that clear? That's to avoid saturation. And somebody's already made this observation. A special case is if we replace that feedback resistor with a wire. And let's just go a little bit, since we enjoy these extremes, let's just let R sub S go to infinity. Now we're essentially removing R sub S from our circuit. And that now provides us with V sub O equaling the output voltage equaling the input voltage, V sub G. And what's the gain? What's the gain between the input and the output in this special case? It's hard because it's staring us as nothing, but it's 1, isn't it? The scalar is 1, and we want to sound fancy, so we call it unity. This is a unity gain voltage follower circuit. Unity gain and the output is following the input. It's a voltage follower. You say right, it goes right. You say left, it goes left. And it moves accordingly. How fast you're moving, it follows nicely. So that leads us smoothly into this buffer circuit. But how do we now connect it up? Under those extreme or special cases, how do we finish this diagram? Is it finished? Remember, this was coming to us from our non-inverting amplifier. We're now putting signal into the non-inverting pin of the op amp through a resistor R sub G. And what did we now say we wanted to do in addition to that? What was the special case? I will make the most difficult labeling. There's our output voltage. But what else do we need to do? Are we finished? We said the feedback resistor was 0. Is that what is shown here? Is it 0? 0 now means R sub F is a wire. The resistance is 0. Not that it's gone. R sub S is gone. Where's R sub S? R sub S used to be right there. That was R sub S. We said it's going to infinity. To infinity and beyond, it's now gone. But R sub F, it's right there. That is now our unity gain voltage follower circuit. We're done. And the output now tracks the input. Because we know this, I sub P is equal to 0. So we have negative feedback. And V sub P is equal to V sub G. And all of these other connections. Now we know that V sub N is equal to, here's V sub N. Well, that's the same as V sub 0. Well, V sub n, because of negative feedback, is the same as V sub p, but that's the same as V sub g. Now you're going, why? Why are we getting so excited about the input equaling the output? Now you might hear this unity gain voltage follower circuit described as a buffer. It's a buffer between the input and the output. Let's see what that means. Let's look at this via an application as a buffer. First, let's look at the scenario when we do not insert this and we have a source. Let's say we now have a source, and you know now how to model a generic source. That's some voltage with a resistor. Let's call that R sub s and the voltage V sub s. And now let's connect that with a load, which we will model as a resistor. Here's our load. And here's V sub L. How is V sub L related to V sub S? Here is our source. It's connected to a load. We have this current, I sub L. What is V sub L? Can you now write down an equation for that? That was exam 1, wasn't it? You now have exam 2 in 9 days. Oh, that got a response. That was better than the V8. Ooh. Maybe not the best response, but what's V sub L? That's a voltage divider. R sub L over R sub L plus R sub S times V sub S. V sub L then is a fraction of V sub S. It's less than, and that's what we referred to as loading. And that's what's happening without a buffer. Let's insert a buffer, which we now know how to build out of an op-amp. Let's insert a buffer between the source and the load. We now have our source. We have our load. And between that, we want to put in our buffer. And our buffer let me put it down just a little bit. There's the plus. Now I'm going to put the minus here. So the minus had the feedback path with R sub F equal to 0. V sub S now is connected through R sub S into the buffer, and we can now go ahead, well, let me just go ahead and make this not quite as busy. I'll just make these now the common connection, so that in fact I could supply this with the negative VCC, and this is now with the positive VCC to reference. Now I've inserted a buffer built from an op amp. Very basic construction. I now just have to wire the inverting pin and the output pin together with a wire. Put the source input into the non-inverting pin and let the output of the op amp drive the load. What does this do for us? What's the voltage at V sub P? Here is V sub P. What's that voltage? Or, to think about that, what is this current? That's going directly into the op amp's input terminal. It's 0. That now says we have no voltage drop across R sub S, the source's resistance. V sub P is now the same as V sub S. What do we know about that op amp buffer? Do we have negative feedback? Yes, we're feeding the output pin back to the inverting pin. What does that give to us, or allow for us to say? Now we can say that we're forcing the two input pins to be the same potential. V sub N and V sub P are the same. V sub P was V sub S. V sub N is V sub S. But V sub N is the same as V sub 0 because of that wired feedback. What's this voltage then, right here? Isn't that V sub S? And isn't V naught the same as V sub L? Does this now tell us that V sub L is the same as our input voltage, capital V sub S? And without the buffer, what was it? What was V sub L? It was less. So now with that buffer, we've put a buffer between the source and the load. Now we can excite the load with the source without reducing the source voltage in the process by this buffer circuit. That's the power of this buffer circuit. Here you can say then that we have no loading. Questions on that? Yes? What if we didn't have an R sub S in that circuit? The question was, what if we did not have an R sub S in that circuit? What is R sub S? R sub S is trying to model the source's internal resistance. So the source is probably going to have some internal resistance, but let's say that you build a source that didn't have any resistance. Great, because then you're not losing any power in your source before you get to the terminals of the source. But is it critical, our analysis, if R sub S goes to 0? No, because we still have 0 current flowing. What if we went the other way? What if we let R sub S go to infinity? You just disconnected your source from anything, right? If you pushed R sub S to infinity, you've now opened it up. So what are you doing? I don't know. You're definitely not exciting your load with that source. Where does that leave us? Now that you're packing, think about this for tomorrow. the difference amplifier. Now we are combining the two pieces that we've already been talking about, the inverting and the non-inverting, all into one. That means we probably have a plus and a minus, a difference. We're going to have a difference amplifier. We'll talk about that tomorrow.